In order to demonstrate the process of balancing a chemical reaction, we want to consider the combustion of methane, CH4, which of course is natural gas. And when we light this Bunsen burner that mixes methane with oxygen, we know that the reactants are, in fact, directly identifiable. They are methane and O2. But we also know, and we will continue to develop our depth of this understanding, that the products are CO2 and water. And so when we envision this, we see these methane molecules coming in through the little tube that's supplying natural gas to the burner. And that burner is sucking oxygen in from the atmosphere around it. And out of that flame comes water and CO2. This, by the way, is exactly what happens when you eat breakfast. You are eating carbon-hydrogen bonds, and you're breathing in oxygen, and when you breathe out both CO2 and water. And so all of these organisms, whether alive or whether we're burning material, all convert carbon-hydrogen bonds into CO2 and water. So now we have to balance these chemical equations. And it's the molecular structures involved as reactants and as products of this reaction that have been established by direct observation, as we've indicated. So we know what appears on the left-hand side of that equation and what appears on the right-hand side of the equation. On the left-hand side, we have methane and O2, and on the right-hand side, we have CO2 and water. The first thing we recognize after writing down what those species are is that that chemical equation is unbalanced. It's balanced with respect to the carbon. There's one on each carbon atom on each side, but there are 4 hydrogen atoms on the left-hand side and only 2 on the right-hand side. There are also 2 oxygens on the left-hand side and 3 on the right-hand side. So we need to balance this. So we begin the process of balancing our chemical reaction by recognizing what's on the product side, which we've already done. That's CO2 and water. And the stoichiometric coefficients, as they are called, are the coefficients that actually balance that chemical reaction. And we need to have the same number of hydrogens, carbons, and oxygens on the left-hand side as we do on the right-hand side. So we've solved the problem with carbon. We've got 1 each on the left and the right-hand side. But now we have to balance the hydrogens. And when we look at this particular representation, we recognize the 4 hydrogens on the left-hand side and the 2 on the right-hand side. So if we multiply water on the right-hand side by the stoichiometric coefficient of 2, we've now balanced the hydrogen atoms. So we've now balanced hydrogen and carbon. And the next question is, how do we balance oxygen in this reaction? We have 4 oxygen atoms on the right-hand side, the product side, but only 2 oxygen atoms on the left-hand side, on the reactant side. So if we multiply the number of oxygen molecules on the left-hand side by a factor of 2, the stoichiometric coefficient of 2, now let's see what we have. We've got 1 carbon on each side. We've got 4 hydrogens on each side. We have 4 oxygens on the left-hand side and 4 oxygens on the right-hand side. So we now have a balanced chemical equation. And we balance that chemical equation with the stoichiometric coefficient multiplying oxygen, the stoichiometric coefficient multiplied by water, and that balances the chemical equation.